Or maybe picture a ball rolling towards a hill. Instead of going over it, it just sort of vanishes into one side and pops out the other without ever having the energy to climb it. Sounds like pure fantasy, right? But in the quantum world, particles actually do something remarkably like that. Welcome to the deep dive. This is where we take complex ideas, break them down, and try to make them genuinely understandable. Today, we're plunging into one of physics' most, well, mind-bending phenomena, quantum tunneling. And our guide for this is a really thorough analysis called quantum tunneling, a refutation of energy boost hypotheses. So our mission today is pretty clear. We're going to figure out how this really bizarre thing actually works. We'll debunk some common myth and explore why some explanations that feel intuitive are actually, well, just wrong. By the end, you should have a really solid grasp of quantum tunneling, cutting through the noise so you can understand one of the universe's, frankly, most surprising concepts.
Yeah, it's fascinating how our everyday experience just completely fails us here, doesn't it? I mean, classically, things are things. They have definite places. A ball needs enough energy to get over a hill, period. It bounces back or it stops. Simple.
Right. No weirdness.
Exactly. But quantum mechanics throws a wrench in that with wave-particle duality. This is the idea that tiny things like electrons or protons aren't just little balls. They also act like spread-out waves. And shifting your thinking to that wave picture, that's absolutely key for tunneling.
Okay, so it's not just a point, it's also a wave. But how do physicists actually describe this wave nature for something like an electron?
Ah, that's where the wave function comes in, usually written as psi, that Greek letter. Think of it like the quantum blueprint for a particle. It's a mathematical object holding all the information you can possibly know about the system.
All the information, like where it is and how fast it's going?
Well, sort of, but it's probabilistic. The wave function itself doesn't say the particle is here. Instead, its value squared CZ2 tells you the probability of finding the particle at a specific spot if you were to look for it.
Ah, okay, so it's about chances.
Exactly, and here's the really deep part. Before you measure, the particle is the wave function. It exists as this spread-out probability distribution. This delocalized, wavy existence is the ultimate reason tunneling can happen. It's not just a fuzzy particle, it is the wave.
Okay. So the wave function describes the particle's probabilistic state. What governs how this wave function behaves? How it changes or moves?
That's the role of the Schrödinger equation. Erwin Schrödinger published it back in 1926. It's really the cornerstone of non-relativistic quantum mechanics. You can think of it like the quantum version of Newton's F-nib. It dictates how the wave function evolves.
So it's the rule book for waves.
Precisely. It connects the particle's mass, its total energy, and any forces it feels, what we call the potential Vx, to how the wave function changes in space and time. When you solve this equation for a situation like, say, a particle hitting a barrier, the solution tells you everything quantum mechanics allows you to know.
Right, let's get back to that barrier. How does this wave function, governed by Schrödinger's equation, explain getting through something it shouldn't, classically speaking?
Good question. Let's picture that particle, energy E, hitting a potential barrier like our hill of height 0. And critically, E is less than 0, not enough energy to get over.
Classically, it bounces off, 100% reflection.
Correct. But quantum mechanically, we solved the Schrödinger equation in 3 regions. Region I, before the barrier. The solution is an oscillating wave. Think sine or cosine. This represents the incoming particle waves and also a reflected wave bouncing back.
Okay, makes sense so far.
Region 2, inside the barrier. Now this is where the magic, well, the quantum mechanics happens. Because E is less than V, the mass changes the character of the wave function. It stops oscillating and becomes an exponentially decaying function.
Decaying? So it gets weaker and weaker the deeper it goes into the barrier.
Exactly. We call this an evanescent wave. It's like a disturbance that doesn't really propagate. It just fades out. But the crucial point is, it's not 0 inside the barrier. There's a non-zero probability amplitude, even in this classically forbidden zone.
So forbidden just means decays rapidly in quantum terms.
Pretty much. For a quantum wave, it's not an absolute stop sign. And then region 3, after the barrier. If the barrier isn't infinitely thick, that decaying wave function might still have a tiny non-zero value when it reaches the other side. Once it's past the barrier, the equation allows it to become an oscillating wave again, a transmitted wave.
So a little bit leaks through.
A little bit leaks through. And here's the kicker. When you solve the math carefully, the wave number k, which relates to the particle's momentum and kinetic energy, is exactly the same in region 3 as it was in region 1.
Wait, the same?
The exact same.
Yeah.
This is direct proof from the Schrödinger equation. The particle's total energy E is unchanged. The particle that emerges on the other side has precisely the same energy it started with. It didn't gain anything to get through.
Wow, okay, that's counterintuitive, but it's clear from the math that energy is conserved. It's purely a wave thing. But how likely is this? Is it common or incredibly rare?
That depends. By carefully matching the wave functions at the boundaries, making sure they connect smoothly, we can calculate the transmission coefficient, T. That's the probability of tunneling. There's an approximate formula for it, which is roughly delio E2 kappa L, where L is the barrier width and kappa depends on the barrier height, DEE, and the particle's mass.
So that exponential term, that means it drops off fast.
Very fast. The probability decreases exponentially if the barrier gets wider, L, or higher, the rho, or if the particle gets heavier, M. This is why you and I don't accidentally tunnel through walls. For macroscopic objects, the probability is astronomically small. It's only significant for microscopic things like electrons or protons.
Got it. And this formula, it only depends on the particle and the barrier, nothing else.
Exactly. Particle mass, particle energy, barrier height, barrier width. That's it. The theory is self-contained. There are no extra terms for, random energy boosts or anything like that. And this completeness, this predictive power, is why the standard explanation is so strong.
And you mentioned this isn't just theory, it's used in real tech.
Absolutely. The scanning tunneling microscope, or STM, it works precisely because electrons tunnel across a tiny gap between a sharp tip and a surface. It lets us see individual atoms. Then there are tunnel diodes in electronics. And it's fundamental to how nuclear fusion works in stars' protons tunneling through their mutual repulsion. Even some types of radioactive decay involve tunneling.
So the evidence is everywhere.
It really is. The standard model just works incredibly well. It makes alternative ideas seem, frankly, unnecessary.
Okay, so we have this solid wave-based explanation where energy is conserved. But let's tackle that other idea head on, the energy borrowing one. It pops up all the time. It feels simpler somehow. Why is that so popular, and why is it fundamentally flawed?
It's popular because it tells a story that fits our classical thinking. Particles are things, barriers are obstacles, so to get over, you need more energy. If it gets through anyway, I must have somehow gotten that energy right, maybe borrowed it.
Yeah, that's the logic. And people often bring up Heisenberg's uncertainty principle here.
They do. The uncertainty principle of delta X, delta P gec bar 2E is fundamental, absolutely. It says you can't know both a particle's position and momentum perfectly at the same time. This inherent fuzziness is related to the wave nature that allows tunneling in the first place. The wave function is spread out, meaning there's uncertainty in position, which is linked to tunneling. But the principle itself isn't a mechanism for boosting energy. It describes the intrinsic nature of the quantum state. It doesn't provide a temporary energy loan.
Okay, so it enables the possibility but doesn't provide the energy. What about the other uncertainty principle, the energy time one? Delta E, delta T goop bar 2. That sounds exactly like borrowing energy for a short time.
Ah, yes. That one gets misinterpreted a lot. In standard quantum mechanics, time isn't an observable, like position or momentum. It's a parameter. So this relation has a different, more subtle meaning. It typically relates the lifetime of an unstable state to the inherent uncertainty or width in its energy. Think of a particle that decays quickly. Its energy level isn't perfectly sharp. It does not mean a stable particle, like our electron hitting a barrier, can just violate energy conservation and borrow energy delta E for a time delta T to hop over. That's a heuristic, sort of appealing story, but it's not what the physics says.
So applying it that way is just wrong.
It's a flawed heuristic. For one, as we've hammered home, energy is conserved in tunneling. The Schrödinger equation solution shows the particle emerges with the exact same energy E. It never had EV.
Right, the math was clear on that.
And second, if you tried to misuse the energy time uncertainty to estimate tunneling, you'd get nonsensical results. Like, it might imply tunneling gets easier through higher barriers because you need to borrow more energy, meaning for a shorter time, which sounds easier. But the reality is the opposite. Higher barriers make tunneling exponentially harder.
So the heuristic leads to wrong predictions.
Exactly. As the source material bluntly puts it, thinking in terms of wave functions means you don't need to talk about borrowing energy. And there's just no such thing as short-term borrowing of energy in this context.
It really shows how careful we need to be with analogies that feel right but don't match the underlying physics.
Definitely. And we can contrast this with something real. Thermal activation. In a hot system, particles are constantly getting random energy boosts from collisions with other particles. They can get enough energy to jump over a barrier classically.
Right, like molecules in a warm gas.
Precisely. But the key difference is temperature dependence. Thermal activation gets much weaker as you cool things down. Quantum tunneling, on the other hand, doesn't rely on temperature. It works even near absolute zero, where thermal kicks are gone. This independence from temperature is strong experimental proof that tunneling is a purely quantum effect, completely different from classical energy boosts.
Okay, that nails the coffin shut on the simple energy boost idea for me. But what about that other grander hypothesis, that the energy comes from interacting with everything else in the universe?
Right, the universal interaction idea, it sounds very dramatic. This concept vaguely echoes something called Mach's principle. Einstein actually coined that term. Mach's principle is this speculative idea, mostly in cosmology and gravity, that an object's inertia, its resistance to being pushed, isn't an intrinsic property, but arises from its interaction with all the other mass in the universe. Like the distant stars somehow tell an object how hard it is to accelerate.
So mass out there affects inertia here.
That's the gist of it. It influenced Einstein when he developed general relativity, and some alternative gravity theories play with this idea. But it's still quite vague and definitely controversial. It's purely about gravity in the cosmos.
So how does that connect to an electron tunneling through a potential barrier in a semiconductor? It sounds like completely different physics.
It is. There's a massive disconnect. Tunneling, as we've seen, is a quantum mechanical effect. It's governed by the Schrödinger equation, involves local potentials, and typically involves electromagnetic or nuclear forces. Mach's principle is classical, cosmological, and only about gravity.
Apples and galaxies.
Pretty much. There's no term in the Schrödinger equation for tunneling that depends on the mass distribution of the universe. The tunneling probability depends only on the local particle and barrier properties. Our source material is quite direct. No, Mach's principle cannot explain quantum mechanics, calling it a fundamental category error.
Okay, but people hear quantum and connectedness and maybe think of entanglement. Is that related at all? Quantum non-locality.
That's a really important distinction to make. Entanglement is a real quantum phenomenon involving non-local correlations. If two particles are entangled, measuring one instantly influences the possible outcomes for the other, no matter how far apart they are.
Like your magic coins example.
Exactly. But, and this is crucial, entanglement cannot be used to send energy or information faster than light. It creates correlations, but you still need classical communication to compare results and see those correlations. It's fundamentally different from a hypothetical universal interaction that causes tunneling by transferring energy. That's just not what entanglement does.
So even the weirdness of entanglement doesn't support this universal energy source idea for tunneling.
Correct. While physicists are searching for deeper theories, like a theory of everything, none of the serious candidates propose Mach's principle as the explanation for quantum tunneling.
It really seems we keep coming back to this human desire for a simple causal story, even if the math and evidence point elsewhere. Did anyone ever try to build a proper theory around that random energy boost idea?
Yes, actually. And it's a really instructive story from the history of physics. The theory is called stochastic electrodynamics, or SED. SED tried to explain quantum effects using purely classical physics, plus one extra ingredient, a real classical fluctuating electromagnetic field called the zero-point field, ZPF, that fills all of space, even at zero temperature.
A background hum of energy everywhere.
Kind of. The idea in SED is that a classical particle is constantly being jostled and kicked around by this random ZPF. And how does SED explain tunneling? Well, it looks remarkably like the intuitive energy boost idea. The particle near a barrier gets random kicks from the ZPF. Occasionally, purely by chance, it gets a big enough kick to just go over the barrier classically.
Because not tunneling through, it's being kicked over by this background field.
Exactly. It replaces the wave function penetration with classical dynamics plus random ZPF kicks.
Okay, that sounds like it might actually work. Did it? How did SED fare against experiments?
Initially, it had some intriguing successes. It could reproduce some simple quantum results, like the behavior of a quantum harmonic oscillator, or explain things like the Casimir effect or van der Waals forces without using quantum mechanics explicitly.
So far, so good.
But it ran into major problems with anything more complex. The absolute killer was the hydrogen atom. SED predicts that the electron orbiting a proton in hydrogen would constantly absorb energy from this zero-point field. It would get kicked harder and harder until it just flies away. The atom would self-ionize.
But atoms are stable. That's kind of fundamental.
Exactly. The fact that hydrogen atoms exist and are stable is one of the most basic observations in physics. SED's prediction of instability is a catastrophic failure.
Mm.
It also couldn't explain interference patterns in experiments like the double slit, which are quintessential wave phenomena.
So the theory that formalized the energy boost idea basically failed a fundamental test.
Yes. Because of these profound disagreements with reality, SED is now considered largely refuted. It's a fantastic example of science at work. Propose a hypothesis, test it, and if it fails the tests, you discard or modify it. SED failed key tests.
It really underscores why the wave function approach, even if weird, is the one that works.
It does, and it's not the only interpretation consistent with the math either. Even if you don't like the standard Copenhagen view, other interpretations handle tunneling without energy boosts.
Like what?
Well, there's pilot wave theory or de Broglie-Bohm theory. It says particles do have definite positions, but they're guided by a real wave. Tunneling happens because the guiding wave penetrates the barrier and steers the particle through. Energy is still conserved.
Interesting. The particle follows the waves of the wall.
Sort of, yes. Then there's the transactional interpretation. It views a quantum event as a complex handshake between waves traveling forward and backward in time. Again, different conceptual picture, explicitly non-local, but energy is conserved. No borrowing needed.
So, multiple ways to think about it. None needing energy boosts.
Precisely. The mathematical core of quantum mechanics, validated by experiment, simply doesn't require that extra mechanism. The wave nature is enough.
This whole discussion really brings it home, doesn't it? That core conflict between our everyday intuition, solid objects, cause and effect, and the strange wave-based reality of quantum mechanics.
Absolutely. The energy boost story feels comfortable because it fits our classical world. But phenomena like tunneling force us to accept the counterintuitive idea of the probability wave as being fundamental. Sometimes, to make progress, you just have to trust the math when it's been rigorously tested, even if it feels weird.
So let's quickly recap the key takeaways.
Okay. First, the standard explanation of quantum tunneling is solid. It comes directly from the wave nature of matter and the Schrödinger equation. Second, a particle's wave function can exist inside a barrier, decaying exponentially, allowing a chance to appear on the other side. Third, and crucially, the particle's total energy is conserved. No gain, no loss.
And the alternatives.
The random energy boost idea. It's a flawed heuristic, violates energy conservation, makes wrong predictions. The universal interaction idea. That mixes up cosmological concepts like Mach's principle with quantum mechanics, a category error. And stochastic electrodynamics, the theory that tried to formalize the energy boost, largely falsified, mainly because it predicts atoms shouldn't be stable.
Meanwhile, the standard quantum theory is mathematically sound, predictive, and experimentally verified across countless applications.
Right. Comparing them. Classical physics needs energy EV euros to cross. Standard QM allows EV ray via wave penetration, conserving energy. SED allows EVOs but needs random kicks from a ZPF, effectively changing the particle's energy momentarily. Only standard QM aligns with all observations.
It really shows that sometimes the deepest truths just aren't intuitive at first glance. Quantum tunneling isn't magic energy, it's just the fundamental waviness of reality asserting itself. It really pushes us to think beyond our everyday limits.